Today, we're diving into a huge breakthrough in battery tech. But here's the twist. The solution isn't coming from some sterile, high-tech lab. Nope. It's coming from rice fields and the ocean. And it might just change our energy future for good.
Think about it. Our entire world, from our phones to our cars, runs on lithium-ion batteries. And I know you felt that pain, right? That frustration when your battery dies way, way too soon. It really feels like for all the incredible leaps we've made, batteries are just lagging behind. So what's the holdup?
Well, for the past 30 years, the core of the problem has been hiding inside the battery itself, specifically in the negative electrode, the anode. In pretty much every lithium-ion battery out there, it's made of graphite. And look, graphite's been a total workhorse, but it has officially hit a wall. It just can't physically store any more energy.
Okay, now this is where it gets really exciting. Scientists have known for ages that silicon is the heir to the battery throne. Just look at that number, a theoretical capacity of 4,200 milliamp hours per gram. That's over 10 times the energy density of graphite. A switch to silicon could mean phones that last for days, or EVs with a range that finally kills range anxiety. But if it's so amazing, why aren't all our batteries made with silicon already? This is why. Silicon has one massive, fatal flaw. And it all comes down to this number, 300%. That's how much silicon expands when you charge a battery. So what does this 300% expansion actually look like in practice? Well, as the battery charges, the silicon anode just greedily soaks up lithium ions, and it inflates like a balloon. Then when it discharges, it shrinks back down. Imagine doing that over and over. This insane swelling and shrinking creates so much stress that the silicon literally cracks, pulverizes, and turns to dust. The whole electrode gets destroyed, and the battery is totally useless after just a handful of cycles. This has been the billion-dollar question for battery researchers for years. The old approach was to try and build these super complex, really expensive nanostructures to cage the silicon and contain that expansion. But what if we've been looking in completely the wrong place? What if the best solution isn't something we manufacture, but something we grow? And that brings us to this key idea, bioprecursors. The thinking is, instead of trying to build these complicated structures from the ground up, why not turn to nature? It's been perfecting tiny, incredibly strong structures for millions of years. We can use these natural blueprints to create the perfect home for silicon. Now, this research is heading down two really cool paths. On one side, you have the sheer abundance of agricultural waste. And on the other, you have the absolutely stunning functional architecture of microscopic algae. So let's start with path number one. Rice is one of the biggest crops on the entire planet, and every year it produces about 150 million tons of waste rice husks. Most of the stuff is just thrown away or burned. But it turns out these husks are packed with silica, which is the raw material you need to make silicon. And this is where it gets really brilliant. You're taking a massive global waste stream and turning it into a high-value, high-tech material. When you burn the husks in a controlled way, you get this ash that's up to 99% pure silica. And the best part? That silica already has a natural nanostructure that, once it's converted to silicon, creates these tiny, porous particles that are way better at handling that destructive swelling. All right, now for the second path. And honestly, this is where things get even more mind-blowing. These are diatoms. They're tiny, single-celled algae that build these beautiful, intricate, geometric exoskeletons for themselves out of silica. They are basically nature's master nanotechnologists. And these shells, they're called frustules, are almost perfectly designed to solve our battery problem. You see, the diatom's shell is a true structural marvel. It's covered in all these little pores that are perfect for letting lithium ions flow in and out. But here's the real magic. That porous cage-like structure acts like a natural shock absorber. It gives the silicon inside empty space to expand into so it doesn't break the whole structure apart. It is literally nature's pre-built solution to the 300% expansion problem. So, how do these two natural solutions stack up? Well, both are super scalable. You've got tons of rice husks waste, and diatoms can be grown at a massive industrial scale. But where the diatoms really shine is in purity and structural control. With rice husks, you get what you get, impurities from the soil and stuff. But with diatoms, you can culture them in a controlled environment, which means you get incredibly high purity and, this is the game changer, control over the structure itself. And this leads to the most exciting part of this entire field. Diatoms have this amazing ability called morphological plasticity. Now, that's just a fancy way of saying they actually change the shape of their silica shells based on the environment they're in. By tweaking things like the nutrients or the temperature of the water they're growing in, scientists can actually guide the diatoms to build the exact architecture they want.
So let's just let that sink in for a second. We're moving beyond just finding useful things in nature. We are on the verge of actually collaborating with it. We're learning how to bioengineer the perfect battery parts by basically asking microscopic algae to build them for us. I mean, that's a huge shift from traditional manufacturing to cultivation.
Of course, we're not quite there yet. The next big steps are to really nail down the environmental benefits with full life cycle studies, to create standard tests so we can compare all these different natural materials, and most importantly, to get material scientists and biologists working even more closely together. So, as we're all looking for the next great leap in technology, maybe the answer isn't about making things more complicated. Maybe the most elegant, the most sustainable, and the most powerful solutions have been here all along, quietly growing in our fields and floating in our oceans, just waiting for us to notice.